Started. I have something to admit, which is that I'm really looking forward to today's lecture. Because today's lecture is the lecture where we discover that all of the differentiation, integration, and so forth that you thought you understood for all of your previous lives as physicists, in fact, you've been doing something completely different. And we're going to be studying today, we're going to be continuing our discussion of tensor calculus, and in particular, we'll complete our discussion of differential forms. And differential forms is a subject that you might think you know nothing about. But in fact, as we will discover today, you have been dealing with differential forms for several years. And scattered throughout your education as physicists, there have been little clues to the theory of differential forms hiding in plain sight, just like a Dan Brown novel. So today is going to be some sort of, better than a Dan Brown novel, but with an editor. So today we're going to be discovering the theory of differential forms, which I think is a really beautiful subject. And then, after our study of differential forms, we'll begin our study of geometry and honest. So today we will learn how to differentiate and integrate, and then following that we will begin studying metrics, studying geometry, leading into next week a real bona fide adventure in the geometry of space-time. So lots of good stuff to look forward to. So let me remind you of where we left off last episode. So a differential form of rank n, or just an n form, is a completely anti-symmetric 0, n tensor. What does that mean? That means that a differential form is a tensor. So, for example, a P form is a tensor of rank P with P lower indices, such that whenever you interchange two of the indices, you pick up a minus sign. So, for example, a scalar is a 0 form. A object with one lower index, namely a covariant vector, is a 1 form. An object with two lower indices, which is anti-symmetric in those indices, is a 2 form. That's what you might think of as an anti-symmetric matrix. And then there are higher generalizations of that with more and more lower indices. But all of these objects are completely anti-symmetric. And we have a special way of multiplying differential forms with one another to get another differential form, which is known as the Wedge product. So if A is a P form with components mu1 up to mu p, and B is a Q form with components mu1 up to mu q, then you can define the differential form A wedge B, which will have P plus Q indices. It'll be a P plus Q form. And it's just given by multiplying those two differential forms together and anti-symmetrizing over all of the indices, along with some normalization factor, which is really just a matter of convention. So, whereas usually in this course we will just use index notation to describe tensors, we'll just write out the indices explicitly. It's often very convenient to use index-free notation. So remember that a 1 form is usually written in index-free notation as omega mu dx mu, And so we can use the dx mu's as a basis of one forms, and then we can use the wedge products of two dx's as a basis of two forms, and so on and so forth. So it's convenient to write down an expression for a two form, for example, as f mu nu dx mu wedge dx nu, and so on and so forth. Okay, now why are differential forms useful? Differential forms are useful because, in fact, differential forms are the types of tensors that can be differentiated and integrated without introducing any geometry, without introducing a metric, without introducing any of that other mathematical structure. So theories of physics which can be formulated in terms of differential forms are rather special. They're sort of non-geometric theories of physics in a sense. Electromagnetism is an example of a theory of physics which can be formulated purely in terms of the language of differential forms. Indeed, if I were to write down Maxwell's equations in the language of differential forms, how would I write them? Well, F is the electromagnetic field strength tensor, and Maxwell's equations are the statement that dF equals 0. Okay. Can't get simpler than that. What here is D? Well, remember last time we introduced the notion of the exterior derivative. So the exterior derivative is a way of taking derivatives of differential forms. So the exterior derivative of a p form is a p plus 1 form. So if A is a p form, then the exterior derivative of it is usually denoted dA. It's a p plus 1 form. And so if we were to write it out in index notation, it's we just take the partial derivative of the tensor A and anti-symmetrize over all of the indices along with some factor, which is just some mathematical convention. And we checked last time that the purpose of the anti-symmetrization was the following. So as you hopefully remember from last time, generally speaking, if you just take the partial derivative of a tensor, you'll get an object with one more lower index, because the partial derivative has a lower index here, but you won't necessarily get something that transforms like a tensor. The reason being that under coordinate transformations, you'll pick up various terms involving the second derivative of the coordinate transformation. However, when you anti-symmetrize and use the equality of mixed partial derivatives, all of those funny terms go away. And so what you find is that if you are willing to restrict your attention only to anti-symmetric tensors, namely differential forms, you can take derivatives in a way which is completely consistent with coordinate invariance and gives you another differential form. So that means that if you use the language of differential forms and you use the exterior derivative as we have defined it here, you can actually formulate laws of physics in a coordinate invariant manner. And so you should not then be surprised that many laws of physics are indeed most easily formulated in terms of differential forms. There's a sense in which the differential form is the most basic structure that you can introduce, which allows you to take derivatives and integrals in a way that is coordinate invariant, independent of your choice of coordinate system. And so, for example, electromagnetism is the prototypical example of a theory which can be formulated in terms of differential forms. So throughout this course, I'll be using electromagnetism as a bit of an example because it's in many ways qualitatively similar to general relativity. Unfortunately, general relativity itself cannot be formulated in the language of differential forms. Well, it can, but only if you're willing to sort of bend over backwards and introduce a bunch of additional structure in addition to what I've done here. But what I would like to do today is just complete our discussion of differential forms. So we've learned how to take derivatives of differential forms. I'd like to investigate this derivative, this exterior derivative, a little bit, and actually show you that it's something that you already know and love very well. And then I would like to teach you how to integrate. And that's where the Dan Brown part of the story kicks in. Because, in fact, the theory of integration that you were taught in your multivariable calculus classes is nothing more and nothing less than the theory of differential forms, the theory of integrating differential forms. So that's where we're headed today. Maybe before we dive in, I should pause and see if there are any questions. I realize that the language of differential forms, when I write things in index-free notation and I write all these symbols, can be a little overwhelming at first. It's just a bit of language that you need to get used to. Yes?
DA, is that all? What is that?
So mu1 up to mu p are indices that take values from 1 up to d, where d is the dimension of my manifold. D here denotes the partial derivative d by dx mu1. And A denotes our differential form. So it has p indices because it's a p form. A is anti-symmetric in all of its indices. If you interchange any two of them, you'll get a minus sign. And when I write the square brackets here, I'm anti-symmetrizing. So this is a sum of a bunch of different terms. So let me write this out a little more explicitly. So for example, if f is a scalar, then df is the one form whose components are, so it's a one form, so it has one component. And that component is the derivative of f with respect to x mu. And indeed, that's a one form. We checked very explicitly about a week ago that that transforms in the right way under coordinate transformations.
Different indexes?
Yes, so remember, so perhaps it would be useful if I worked this out a little more explicitly. So, for example, if you have a one form omega, that's a guy with one index. And if you take d of it, you get a two form. So what is that? That is the tensor with components d mu omega nu minus d nu omega mu. So I'm anti-symmetrizing over those two indices. There is a factor of 2 coming from here, but if you remember my definition of anti-symmetrization, there was a factor of 1/2. So hopefully everything cancels out there. Now, if I have 3 indices, how many ways are there of permuting 3 indices? Well, there are 6, if I remember correctly. So, for example, if you have a 2 form, f mu nu, and you take d of it, you get a 3 form. So there's 3 indices. What are those? That's d mu f nu rho minus d nu f mu rho plus d nu f rho mu minus so on and so forth. There are 6 terms there. Now f itself is a 2 form, which means that f rho mu is equal to minus f mu rho, for example. So there's some simplifications when you write this all out. And there's also some overall coefficient out front because there's a 3 coming from this term here, but then in the definition of anti-symmetrization, there would be a 1/3 factorial. So in fact, there's a 1/2 here. So, you know, you need to be a little careful to get all the factors right. I won't be terribly careful because I have a PhD. I don't need to be careful. You do not have PhDs yet, so you need to be careful when you work this all out. So hopefully that answered your question, made it a little more explicit. Okay. So let's stare at this formula for a second. So there's one obvious identity that this exterior derivative has. Let's imagine that we have a p form, and we take d of it, and then we get a p plus 1 form. So let's take d of it again. What happens? Well, now you have two derivatives that you're taking the derivative of the form over, and you're anti-symmetrizing them. But by the equality of mixed partial derivatives, when you anti-symmetrize two partial derivatives, you get 0, right? So, for example, d squared of a will be a p plus 2 form, which will have some coefficient out front, times d mu 1, d mu 2, a mu 3, all the way up to mu p plus 2. And you'll be anti-symmetrizing, but when you interchange these two indices, you get, d mu 1, d mu 2 is equal to d mu 2, d mu 1 by the equality of mixed partial derivatives. So this is just equal to 0. So what does that mean? That means that this differential operator that we have defined acting on p forms squares to 0. So what do we have here? We have here a bunch of differential forms that we can multiply together using the wedge product, that we can take derivatives of using this exterior derivative. This all is looking probably a bit unfamiliar to you. So in fact, what I would like to do is tell you that this is a structure that you have all seen before, and that in fact you are quite familiar with. So what I would like to do is show you that in fact you already know these operations. You already know the exterior derivative and the wedge product. For the special case of flat three-dimensional space. Flat three-dimensional space is a space you have spent quite a bit of time in your classes on multivariable calculus, electromagnetism, and so forth. So what I would like to do then is show you that you already know about these objects in 3 dimensions. Perhaps you've already guessed where I'm going here. But before I do that, let me pause and see if there are any questions. Yes? So mu, usually if we're talking about space-time, I'll take mu to run from 0 to 3. If I'm considering a simple example such as flat 2-dimensional space, I would take mu to run from over 1 and 2. 3-dimensional space, 1 and 3. If I were feeling ambitious and wanted to consider an 11-dimensional space, it would go from 1 to 11 or 0 to 10. It depends on the context in which you're using it. You should imagine that when we're talking about space-time, it runs from 0 to 3. But that, in general, it runs over all the dimensions of the manifold that we're considering. Okay. So what do differential forms look like in 3 dimensions? So remember, that in d dimensions, a differential form a differential form of rank p has d choose p, which is to say d factorial over p factorial times d minus p factorial independent components. Because you have d choices for the first index, d minus 1 for the second index, and so on and so forth. And that's all captured by this binomial coefficient, d choose p. So what do differential forms look like in R3? Well, In R3, you have zero forms. So what is a zero form? A zero form is something with, it's just a function, and so it's just what you would have called a scalar in your classes on multivariable calculus. Okay, that's all pretty simple. What is a one form? Well, a one form is something with three indices. That's what we would have called a vector. Now, what's a two form? Well, a two form is an object with two indices that is antisymmetric in those two indices. And so there are three choices of such object. And so we also call those vectors in our classes on multivariable calculus. You know, F12 you would call, F3, for example, or F13 you would call F2, and F23 you would call F1. So a completely antisymmetric, let's put it this way. An antisymmetric 3x3 matrix has 3 degrees of freedom. And so you would package those into a vector. And so in your classes on multivariable calculus, you also encountered two forms, but you called them vectors. You didn't call them two forms. And you also encountered three forms. Well, there's only one tensor which has which is antisymmetric in all three indices in 3 dimensions. It's the tensor with indices 1, 2, 3. So there's only one of those. And so that's also something that you encountered in your classes on multivariable calculus. You just called them scalars. Now, sometimes in your classes on electromagnetism, you might have noticed that there are actually 2 different kinds of scalars, and there are 2 different kinds of vectors. Sometimes these go under the name of vectors and pseudo-vectors, or scalars and pseudo-scalars, depending on their transformation properties under reflection. And in fact, that language just reflects the fact that there are secretly 2 different types of objects that you are calling vectors, and 2 different types of objects that you're calling scalars. So, what are the multiplication and derivative operations that are the exterior product and the wedge product acting on these guys? Well, for example, how would you multiply a zero form and a one form, a scalar and a vector? Well, you just multiply them together. Likewise, if you want to multiply a zero form and a two form, or a zero form and a three form, you just take that scalar and you multiply it times the vector or scalar to get another scalar. How, then, what about the wedge product of more interesting objects? So the wedge product, remember, takes a P form and a Q form to a P plus Q form. So the wedge product, for example, tells us that we have a way of multiplying a vector and a vector in order to get another vector. So, for example, if you take the wedge product of 2 one forms to get a vector, then it's a way of multiplying 2 vectors to get another vector. And moreover, remember that the wedge product is antisymmetric. So when you switch the two, A wedge B is equal to minus B wedge A when we're talking about one forms. So let us think back and remember if we encountered a way of multiplying 2 vectors together to get another vector. If you think about it, hopefully you'll remember that this is just nothing more than the cross product. In fact, the wedge product is something that you're very familiar with in the context of 3 dimensions. It's nothing more or less than the familiar cross product for the case where you multiply a one form and a one form together. Now, how about a one form and a two form? So when you wedge together a one form and a two form, you should get a 3 form. So that means that you should find a way of multiplying a vector and a vector together to get a scalar. Well, you also know a way of multiplying a vector and a vector together to get a scalar. That's the dot product. So lambda going on a 1 form and a 1 form to a 2 form is a cross product. Lambda, the wedge product for a 1 form and a 2 form to a 3 form is the dot product. All of the various, this wedge product is nothing more or less than a generalization of the notion of a cross product and a dot product to higher dimensions. So the wedge product is just a generalization of the cross product. Indeed, if you happen to have learned multivariable calculus out of a very old-fashioned textbook, they wouldn't have used the symbol x for the cross product. They would have, in fact, used a wedge symbol for the cross product. Maybe you have encountered that at some point in some old-fashioned books on electromagnetism or multivariable calculus. Okay, what about the derivative operator? So the derivative operator takes a 0 form to a 1 form. So that means that there must be some sort of derivative operator which takes a scalar to a vector. Likewise, there's a derivative operator on 1 forms which takes a vector to a vector, and a derivative operator on 2 forms which takes a vector to a scalar. And because we're in 3 dimensions, the derivative operator on 3 forms just gives you 0, because there's no such thing as a 4 form, because there's no completely antisymmetric 4-index object in 3 dimensions. So how do you take a derivative of a scalar to get a vector? Well, that's what we would have called the gradient. How do you take the derivative of a vector to get another vector? That's what we call the cross product. And how do you take the derivative of a vector to get a scalar? That's what we would have called the divergence. So you can see that every single way of multiplying or taking derivatives of vectors or scalars, which you thought were completely different objects, you would have thought that the curl and the gradient and the divergence and the dot product and the cross product were all different things. They were all introduced as different operations in your class on multivariable calculus, but they're all the same frickin' thing when you think about the language of differential forms. They're all just the exterior derivative or the wedge product. Yes?
You did the difference between a vector and a pseudo-vector, but what about the products into normal vectors?
Yeah, we haven't gotten to that. Yes. So also in 3 dimensions, implicitly you're using the fact that you're in a flat 3-dimensional space and you have a metric, and so you also sometimes use the metric to do other things that I haven't introduced yet. So we'll get to that. So we'll get to that probably by the end of this class or early next class. Good question, though. Okay. Now, I told you that d squared was equal to 0. I didn't tell you. I proved it to you. So let's check that that's the case. So what does that mean on a 0 form? That means that the curl of a gradient is equal to 0. That's probably something that you spent a lot of time puzzling over and trying to prove in your class on multivariable calculus. It's a true statement. And instead of just, it's something that's kind of obvious, kind of obscure and hard to remember in the language of multivariable calculus, that becomes completely obvious in the language of differential forms. Likewise, on 1 forms, it says that the divergence of a curl is equal to 0. That's also a true statement. It's true for exactly the same reason, because d squared is equal to 0. I bet you thought that those were different identities, the curl of a gradient and the divergence of a curl, but in fact it's the same thing. So you should really think of this exterior derivative and the wedge product as higher dimensional generalizations of the curl and of the cross product and gradient operator that you encountered in your classes on multivariable calculus. Now, there's a lot more that we could do involving differential forms. There are, in fact, other sorts of operations that one can introduce. So, for example, there's the so-called Leibniz rule. So what do we mean when we say Leibniz rule? The Leibniz rule is another name for the product rule. The derivative of the product is equal to the derivative of the first times the second plus the derivative of the second times the first. That rule gets slightly altered when you're dealing with differential forms. This is rather easy to show. I won't bother proving it. But there's a funny minus sign that creeps in to the Leibniz rule when dealing with differential forms. So this, for example, is something that you're familiar with in the context of three-dimensional calculus. So, for example, if you took the curl of the product, if you took D of the product of a 0 form and a 1 form, for example, in the language of multivariable calculus, that would be the curl of a scalar times a vector, which, according to this formula, is the cross product of the gradient and the vector plus the scalar times the curl of the vector. So, for example, this Leibniz rule incorporates all of those various rules that you labored over in your classes on multivariable calculus. Yes? P is the rank of the A form. So A here is a P form and B here is a Q form. The number of indices. Yes. I'm using the same notation that I've used above, where A is a P form. Yeah. Okay, so we've learned how to take derivatives. Are there any questions on derivatives? I can't overemphasize the importance of the theory of differential forms. Once you know about differential forms, you realize that they appear everywhere. The theory of mechanics, the theory of phase spaces, and the Hamiltonian evolution of phase spaces is actually a theory of differential forms. Thermodynamics, Maxwell's relations, the theory of the infinitesimal changes of the thermodynamic variables of a system is actually a theory of differential forms. Electromagnetism is really actually a theory of differential forms. And it's kind of hard, once you start thinking about it in terms of differential forms, it's kind of hard to think about it in any other way. So differential forms really appear everywhere. They're kind of the most basic structure out of which you can build laws of physics. Now, in physics, we like to do more than just take derivatives. Sometimes, if we're feeling saucy, we even like to integrate. Now, I've emphasized a great deal so far in this course the importance of writing down only those formulas which are coordinate invariant and which have a meaning which is independent of the coordinate system that one uses to write the law, the equation. So let's imagine that we wanted to perform an integral. It's the sort of thing we might want to do in physics. If we want to write down an action, that's defined as an integral. If we want to calculate the charge of something using Gauss's law, that's defined as an integral. If we want to, integrals are things that we like to do because we like formulating laws of physics. So let's ask how we define an integral. So in multivariable calculus, what did we learn to do? We learned that we were supposed to integrate functions. And in particular, we learned to integrate scalars. So how does the integral of a scalar look when you perform a coordinate transformation? So let's imagine that I have some scalar f of x, and I'm integrating it, and I want to write down that expression in a given coordinate system. So f of x refers to the function written in the x mu coordinate system. So I would write that out a little more explicitly as the integral of f of x dx1 all the way up to dxd if I'm in d dimensions. And the important point about this symbol is that this expression does not transform in a coordinate invariant manner under a coordinate transformation. Instead, this integral will pick up a Jacobian determinant. So it's equal to, if you remember the Jacobian formula from your class on multivariable calculus, it's equal to f of x prime times the determinant of the Jacobian dx mu by dx mu prime times dx1 prime all the way up to dxd prime. In fact, this is the first time probably in your lives that you encountered the Jacobian matrix. It was in the context of the integral transformation formula in multivariable calculus. So the integral formula that you learned for scalars in multivariable calculus actually was something that was not a coordinate invariant quantity because it transformed in this funny way. And that is a sign. That is a sign of the fact that scalars are not what you should be integrating. In fact, if you look at the slide, there are clues hidden all over the place as to what the right quantity to integrate is. In particular, what the symbol is telling you, what the slide is telling you, is that the right thing to integrate over a d-dimensional manifold is a d-form, not a scalar. I've written it for you right here. Look at that equation. It says f of x dx1 times dx2 all the way up to dxd. That's the expression for a differential form of rank d written using the coordinate independent notation in terms of the wedge product of the dx's. All I've done there is I've forgotten to write the little wedge symbols. So let's work this out a little more explicitly. So a D-form has one independent component It has one degree of freedom. So you could be forgiven for mistaking it for a scalar. But a D-form is not a scalar. So a D-form could be written in coordinate invariant language. So if I were to write it in a given coordinate system, it would be omega of x times the wedge product dx1 all the way up to dxd. So that's another way of saying it's the completely antisymmetric object in D indices, the completely antisymmetric tensor with D lower indices such that omega 1 up to D, so omega 1 up to D is equal to omega of x. Okay, so now let me define the integral of this D form as follows. So the integral over our d-dimensional manifold of omega. So M here is just the manifold that we're considering, is the integral of omega of x times dx1 wedged all the way up to dxd. I haven't done anything here. All I've done is write down our formula for omega. And my claim is that the correct definition for this integral is to forget the wedge symbols and just treat this like you would a normal integral in multivariable calculus. So this is the definition of the integral of a D-form. And my claim is that this expression is completely coordinate invariant. Why is it going to be completely coordinate invariant? Well, because we saw that the measure factor, when we perform an integral in multivariable calculus, transforms with the determinant of the Jacobian. And I will now show you that if you write out a D-form in component notation, as I have done so here, in fact, that also transforms with that identical factor of the determinant of the Jacobian. So in your multivariable calculus class, when you learned that integrals under a change of coordinates picked up this determinant of the Jacobian matrix, all you were doing was you were actually secretly learning that the right thing to integrate over a manifold is a D-form, not a scalar. That's what I'm going to show to you. Before I do so, are there any questions? No questions? Okay. Well, let me continue. Feel free to interrupt if you have questions. So how does this D-form change under a change of coordinates? Well, let's imagine that we have some D-form, and let's write out this form explicitly in a given coordinate system. So what does this look like in a different coordinate system? Well, if we want to work it out explicitly, we could just use the fact that dx1, for example, is equal to dx1 by dx mu prime, dx mu prime. So this will be so that's just the usual transformation law for the infinitesimal displacement dx1. So this is the product of d Jacobians, so dx1 by dx mu1 all the way up to dxd by dx mu d times the wedge product dx mu1 all the way up to dx mu d. Now, let's stare at this guy here. Well, what is that guy? Oh, sorry, there are primes there. Is that why you're raising your hand? Yeah, okay. What is that guy? That's the completely antisymmetric wedge product of dx1 up to dxd, possibly with a sign depending on the ordering of the indices mu1 prime up to mu d, with a plus sign if it's an even ordering of 1 up to d, and a minus sign if it's an odd ordering of 1 up to d. And so what is this guy? And moreover, it's completely antisymmetric in the indices mu1 prime up to mu d prime. And what is this guy? This guy is the product of d elements of the Jacobian matrix dx mu by dx mu prime. And it's the product which is completely antisymmetric in all of its indices, the lower indices. Now, if you have a d by d matrix, and you're looking for the product of d elements of that matrix, which is completely antisymmetric in all of the indices of that matrix, there's a name for that product. We call that, the name that we give to that product is the determinant. If you think about what the determinant is and how the determinant is defined, you'll see that, in fact, that's precisely what the determinant is. If that's not clear to you, work it out for the case of a 2x2 matrix, and then remember that the determinant can be defined recursively for a d by d matrix in terms of a d minus 1 by d minus 1 matrices. So this is nothing more or nothing less than omega of x times the determinant of the Jacobian matrix dx mu by dx mu prime times dx1 prime all the way up to dxd prime. And indeed, you remember that in the determinant there are all of those funny plus and minus signs that arise depending on whether we're looking at an even or an odd permutation. Those are nothing more or less than the plus or minus ones that appear in this expression over here. I encourage you, if this is not clear, to work this out for the explicit case of a 2-form, and you'll indeed see that it's precisely the determinant of the Jacobian matrix that appears. You know, generally speaking, if something's true for 2x2 matrices, it's always true, right? I mean, that's generally a good rule to live by. Unless you're studying the CKM matrix. And so what is this here? This is W of x prime. So all we've done is work out explicitly the transformation law for a D form written out in component notation. So that means that if you remember our definition of the integral of a D form, so that's the integral of omega of x dx1 all the way up to dxd, which, using our Jacobian transformation formula that we learned in multivariable calculus, is the integral of omega of x times the determinant of the Jacobian matrix dx by dx prime times dx1 prime by dxd prime. That's just equal to the integral of omega of x prime, the component of this D form written in the primed coordinates, times dx1 prime all the way up to dxd. So this form for the integral is a coordinate invariant definition of the integral. So the only thing that you can integrate over a d-dimensional space to obtain an expression that's independent of the coordinate system that you use to write it is a D form. So the only way, or let me say this a little more properly, the only quantity which can be integrated over a d-dimensional space is a D form. Now, when we introduce metrics and geometries, we will see that, in fact, there are ways of obtaining D forms from scalars and vectors and other sorts of things. But in all of our discussion of integration, it'll all return back to this basic fact, that the only thing that you're allowed to integrate over a d-dimensional space is a D form. So, for example, if we wish to integrate over all of space-time, for example, to define an action, then what we actually need to integrate is a 4-form, because space-time has 4 dimensions. Likewise, if you ever want to integrate over the world line of a particle, what you must integrate is a 1-form. So, for example, a 1-form can be integrated over a world line. Now, in the language of vector calculus, what that would mean is that a vector can be integrated along a path to get a coordinate invariant answer. And indeed, you probably saw this in your classes on multivariable calculus, That's what you would have called in your multivariable calculus class a line integral. Or sometimes you would call it a contour integral. So the integral along a path of w mu dx mu is a coordinate invariant object that you can write down when you formulate your laws of physics in a coordinate invariant manner. You might call that the path integral of omega or something like that, if you wanted to use some fancy notation. There's one other formula that I can't help mentioning, because once you see this formula written in this language, you will never be able to unsee it. So Stokes' theorem is one thing that I can never remember, unless I write it out in the language of differential forms. So let me just tell you what it looks like in this language. So Stokes' theorem is something which says that if you have a integral of a derivative on the interior, then you can of some space, then you can relate that to an integral on the boundary of that space. So I can never. Who the hell can remember what Stokes' theorem looks like in the? There's all these different variants of Stokes' theorem in multivariable calculus. There's one-dimensional Stokes' theorem, which you call the fundamental theorem of calculus. There's a two-dimensional version. There's the three-dimensional version, which goes under the name of Stokes' theorem or Green's theorem, or I don't know, who the hell can remember all that stuff? The nice thing about the language of differential forms is that there's nothing to remember. Because once you remember that the only derivatives that you can ever take are exterior derivatives, the only thing that you can ever integrate is a D form, then there's only one possible formula you can write down, and it happens to be correct. So let's imagine that we have a manifold M with a boundary B. Then if we integrate over M the derivative of some form, so M will have dimension D. So omega here will be a D minus 1 form, so that when you take D of it, you get a D form. And if we were to integrate the derivative of omega over M, that is equal to the integral over the boundary of omega. No mucking around with normal derivatives, with normal vectors, with vector symbols, none of that. This is just the right formula. So for example, in vector calculus, this will lead to the formula, for example, the integral over some volume of a divergence is equal to the integral over the boundary of the normal vector dotted into V. And then all of the other variants of Stokes' theorem and Green's theorem and all that other stuff all follows from this formula applied in various contexts. This formula is lovely in electromagnetism, for example, because I told you that electromagnetism can be formulated in the language of differential forms. So this is the thing that allows you to write down Gauss's law in 0 lines or 1 line using the language of differential forms. So this completes what I had planned to say about the theory of differential forms. Perhaps it's just worth giving a little bit of a recap. So far, we know how to multiply, take derivatives of, and integrate differential forms, but not more general tensors. So the operations of exterior derivative and integral are general operators that exist independent of the geometry of space-time, of the geometry of our manifold. I never introduced any notions of geometry when I wrote down the wedge product, the exterior derivative, and so on and so forth. Unfortunately, or fortunately, I think, in order to understand more general derivative operators and integrals, we're going to need to study some geometry. So, in particular, to take derivatives or to integrate other tensors, what we're going to need to do is understand some geometry. We need to understand what a metric is and what its implications are for the geometric structure of space. And that's where we're going now. But before we do so, I'd like to pause and see if there are any questions. So yes, there was a question.
About the Stokes theorem that you have like the integral over differential form equals to the integral over W. What is like W?
So M is a d-dimensional manifold. Its boundary will have one less dimension. And omega will be a d-1 form. That's the only thing it could be in order for this formula to make sense. The lovely thing about the language of differential forms is that many incorrect formulas are impossible to write down. You always want a notation. In physics, you always want to introduce a notation which makes it impossible to write down incorrect formulas. Unfortunately, it's still sometimes possible to write down incorrect formulas.
So we have the integral of d form and that is equal to integral of d-1.
The integral, yes. The integral of a d form over a d-dimensional manifold is the integral over the boundary of a d-1 form. So, this is not something that, this is a theorem that you've encountered in a variety of contexts over your life. In the context of, one dimensions, it's the fundamental theorem of calculus. In the context of two dimensions, I guess it's Cauchy's theorem. I guess that's right. In the context of three dimensions, it's Stokes' theorem. In the context of four dimensions, it's what I have written here. Yes, question?
You said before that physical theory can be written in the language of differential forms. It says something very deep about the theory.
Yes.
Other than the fact that it's somehow unrelated to geometry, is there anything else we can tell about that?
Well, what I didn't want to go too much into that statement. If you can define a theory of physics without thinking about the geometry of space, it means the theory is topological in some sense. What does topology mean? It means just what I said. It means it has nothing to do with the geometry. So it's true that the differential form and integral, as I've defined it here, are the most basic objects. They are the basic objects that you can think about, which transform in a coordinate invariant way that allow you to write down laws of physics that don't depend on the coordinate system you use. And if you don't have if you don't want to introduce any geometry, that's all you get. Any law of physics, which can be any law of this is the deep principle. Any law of physics that does not depend on geometry must be formulated in the language of differential forms. That's just a true statement. Now, secretly, most every law of physics that you ever write down depends on the geometry of space. So certain laws of physics don't. Maxwell's equations, or at least part of Maxwell's equations, don't depend on the geometry. I wrote down part of Maxwell's equations here, df equals 0. In fact, those were only half of Maxwell's equations. The other half of Maxwell's equations, the ones which have source terms on the right-hand side, they actually do depend on the geometry, but they depend on it in a very, very mild way. So if this were a longer course and I had more time, I would introduce, there's more lovely stuff that one can do with the theory of differential forms, which I won't do here. It's not an accident that topology is, in a sense, the study of differential forms. It's called, so I won't go into that in any more detail. Yes. Any other questions? For example, a lot of you were in my quantum mechanics class last year. When you derived the quantization of charge using Dirac's argument about gauge transformations, I encourage you to try and reformulate that all in the language of differential forms. So, for example, a gauge transformation, if A is the electromagnetic, actually you'll do this in a later exercise in this course. If A is the electromagnetic potential, that is regarded as a one form, and F is the electromagnetic field strength, which is a two form, which is dA, then the gauge transformations are transformations A goes to A plus d lambda, where lambda is a one form, a zero form. The fact that d squared is equal to 0 is why these gauge transformations leave the electromagnetic fields unchanged. And then you can do things like, for example, write down the total charge is nothing more or less than the integral of f over some 2-sphere out at infinity, and so on and so forth. You can do everything completely elegantly and without using any indices whatsoever, using the language of differential forms. But let's not do that here. You'll do, there's a later problem set where you'll, when we discuss general relativity, where you'll work out a lot of this stuff for electromagnetism in more detail. Questions? So I understand that there is probably a sense in which you're feeling a little overwhelmed by the notation and the abstractness of what we have seen. If it's any consolation, the content of the last 3 or 4 lectures would, in the math department, be the content of an entire course. It would usually be a course called Analysis on Manifolds or something like that. If you taught it if you took it in the math department, they would spend their time doing silly things like partitions of unity and proving theorems. We, however, are above or below proving theorems, depending on which way you look at it. We just care about what's true, not whether or not we can prove it. We leave that for other people. Okay, so having completed what in a math department would be an entire course on analysis on manifolds, in the next week and a half or 2 weeks, let's complete what would be an entire graduate math class on differential geometry. Now, of course, the reason we can do it in 2 weeks instead of a semester is that we won't prove things, we will just understand them. So what I would like to do now is begin our discussion of geometry. And in particular, I would like to understand what it means for space-time to have a metric. So we've met the metric several times before in this course, but I would now like to revisit the metric of space-time using the language of tensors that we've spent the last week and a half or so introducing. So let me remind you that from the Einstein equivalence principle, we concluded that space-time is a manifold. In particular, it's a 4-dimensional manifold. And it comes with a metric that is used to define the invariant line element. So the line element, ds, is what you integrate in order to measure the invariant interval along some world line. And it's given in terms of the metric by g mu nu dx nu, where dx mu are these infinitesimal displacements, and g mu nu will be some function of the x mu's in some coordinate system. So here I'm using some coordinate system x mu. And what special property does this metric have? Well, the special property that it had, based on the equivalence principle was that for any point, say x naught, then we can find some coordinate system which has the property that near the point x naught mu, g mu nu is given by the flat Minkowski metric plus terms which are subleading. Now, of course, g mu nu can't be given exactly by eta mu nu everywhere, or else space-time would just be flat Minkowski space, and there would be no gravity. So that would be fine if we only ever had to discuss constant gravitational fields, which are related to flat space-time by a coordinate transformation involving constant acceleration. But of course, life is more interesting, and we'll need to discuss gravitational fields that are not constant. Question?
Is that a bit like Taylor expanding G mu nu?
It is more than a bit like Taylor expanding G mu nu. It is precisely Taylor expanding G mu nu. Now, I should make a point that the coordinate system which makes G mu nu look like the flat metric around one point might not be the same as the coordinate system that makes G mu nu look like the flat coordinates around a different point. And indeed, we will go through the exercise when we discuss the Riemann tensor and curvature. We'll go through the exercise of Taylor expanding the metric very, very carefully. Yes. So you should think of, when I say subleading here, you should think of that in the sense of a Taylor expansion. Good question. Okay. So what precisely is this tensor G mu nu? Is this metric G mu nu? So the metric G mu nu is a 0, 2 tensor with the following special properties. So the first property that the metric has is that it is a symmetric tensor. G mu nu is equal to G nu mu. In particular, it's not a two-form. It's the opposite of the two-form. It's symmetric instead of anti-symmetric. The second property that the metric must have is that as a 4x4 matrix, or a d by d matrix, if you happen to be studying general relativity in a different number of dimensions, G mu nu is invertible. Or, in other words, the determinant of G mu nu as a 4x4 matrix is non-zero. That's another way of saying it's invertible. And finally, because G mu nu is invertible, it can be diagonalized. And so it is diagonalizable and the eigenvalues of G mu nu, namely the diagonal elements, when it's diagonalized, are -1, 1, 1, and 1. I claim that all three of these properties are a consequence of the fact that G mu nu can be written as, in an appropriate coordinate system, as eta mu nu plus terms that are subleading as we move away from the point x naught. So the fact that G mu nu is a tensor just follows from the general principle of coordinate invariance of our laws of physics, namely they have to be formulated in terms of tensors, and these three properties follow from the Einstein equivalence principle. So to see this, let's investigate more carefully the statement that G mu nu can be written as eta mu nu plus subleading near a given point. Well, what does this mean? This means that in any other coordinate system, say some primed coordinate system, the components of the metric will be given by dx mu by dx mu prime times dx nu by dx nu prime, eta mu nu plus terms which are subleading. Or in matrix notation, sorry, there's a prime there, or in matrix notation, this would be the statement that as a 4x4 matrix, G is given by the Jacobian matrix transpose times eta times the Jacobian matrix. Now, eta, of course, is the metric of flat spacetime, which has these three properties, 1, 2, and 3, I wrote at the top of the screen. Eta is symmetric, invertible, and diagonalizable with these eigenvalues. And so if G is related to eta by conjugation by this Jacobian matrix, then G must have these properties as well. So, since eta has these properties, namely, it is a symmetric matrix, it has non-zero determinant, and it has eigenvalues minus 1, plus 1, plus 1, plus 1, so must the metric G. Another way of saying that is that these properties 1, 2, and 3 here are coordinate invariant statements. In the sense that if you have a tensor which is symmetric in one coordinate system, it's symmetric in all coordinate systems. Likewise, if a tensor is invertible in one coordinate system, it's invertible in all coordinate systems, and so on and so forth. So this third property, namely that the metric is diagonalizable with eigenvalues minus 1, plus 1, plus 1, and plus 1, actually has a special name. So property 3 is the statement that spacetime has signature minus plus plus plus. Or there's another version of that statement, i.e. it's the statement that spacetime is pseudo-Riemannian. A Riemannian manifold would be a space with purely positive signature, so that the eigenvalues of the metric were positive numbers, and a pseudo-Riemannian manifold is one with one or more negative eigenvalues. Any questions on that? So we see that the metric of spacetime is not just any 0, 2 tensor, but it's a 0, 2 tensor with these special properties, namely, most importantly, G mu nu is symmetric and invertible. And what I would like to do then is use these properties to make our life simpler. Any questions before I do this? Yes?
So we said G mu nu is invertible, you mean around the point x naught for every point x naught?
For every point x naught, G mu nu is so G mu nu is a set of 16 functions defined for each point in space-time, and at each point it's an invertible matrix. Now the form of that invertible matrix might be different depending on what coordinate system you're using. And indeed, if you use a coordinate system which degenerates at a particular point, one signature that the coordinate system is degenerating is that the metric will fail to be invertible at that point. So if the metric fails to be invertible at a point, there are a couple things that could be happening. The most likely thing that's happening is that you're using a coordinate system that's going bad at this point. If you remember the form for the metric in flat space in polar coordinates, the metric has a 0 eigenvalue at r equals 0 in polar coordinates. The components of the metric are 1 r squared in polar coordinates, and so it has a 0 eigenvalue at the origin. That's not a signature that the origin is a particularly horrendous place. It's just a signature that your coordinate system has gone bad there. Remember that usually we demand the Jacobian matrix has non-vanishing determinant, but the Jacobian matrix for the transformation between Cartesian and polar coordinates had 0 determinant at the origin. So that's a sign that your coordinate system is going bad there. However, it might also be the fact that something deeply wrong is happening to space-time at that point, and it's not just a coordinate artifact. So, for example, when we study black holes, we'll discover that the singularity at the core of a black hole is another place where this sort of thing will happen. Question?
What is the fact that the eigenvalues are minus 1 plus 1 plus 1 plus 1 implies the determinant of the matrix can say it's 1 minus 1?
The determinant is minus 1. Well, the determinant depends on what coordinate system you're using. The determinant of the metric is not a scalar. It depends on what... We'll see this very explicitly. So the determinant of the metric, it doesn't really... The determinant of the metric doesn't have any physical meaning in and of itself, because it's not a scalar. It's a negative number. Let's put it that way. Its sign can't change, but its absolute value is not a number with any coordinate-independent meaning. But it is something which can be combined with other things to have a coordinate-invariant meaning. When we discuss integration, we will see this very explicitly.
But the eigenvalues coordinate-independent?
The eigenvalues, well, yes. Let's put it this way. I can find a coordinate system where the eigenvalues are minus 1, 1, 1, and 1. I could always choose another coordinate system where I rescale all my coordinates by a factor of 2. Okay? In that case, the eigenvalues would be a half, a half, a half, a half, minus a half, a half, a half, a half. The determinant is changed by a factor of 16. So yes. I should, if I wanted to be more properly, I should say that G mu nu is diagonalizable with eigenvalues, one of which is negative, the rest of which are positive. Because the actual value, I can find a coordinate system where the eigenvalues take this form, with minus 1, 1, 1, and 1, but that's not a particularly important statement. It's the signs that are important. You can check, and I encourage you to do so, that that whenever you do a coordinate transformation, even though you might change the values of the eigenvalues, you could never change the number of positive and negative signs. Good question. Other questions? Okay. Let me continue. So I would now like to introduce a little bit more notation. It's a very important notation that we will be using for the rest of this class. So since the metric G mu nu is invertible, we can find its inverse. Now, I won't write down an explicit formula for its inverse in general, because I don't know an explicit formula for the inverse of a D by D matrix in general. So let me just write down a symbol that will denote its inverse. We will denote its inverse by G mu nu with 2 upper indices. So pay attention carefully. It's easy to get confused with this notation. By G mu nu with 2 lower indices, we mean the 0, 2 tensor, which is the metric. And by G mu nu with 2 upper indices, we mean its inverse. So the first thing, of course, that you want to check is that G mu nu is a tensor, and indeed, it's reasonably easy to check that G mu nu, as defined as the inverse of the 0, 2 tensor, which is the metric, is a 2, 0 tensor. And in fact, because G mu nu is symmetric, its inverse is symmetric as well. So G upper mu nu is a symmetric 2, 0 tensor. And G mu nu is the with 2 upper indices is the inverse of the metric with 2 lower indices. So let's just write out the equations which say that G upper mu nu is the inverse of G lower mu nu. So G upper mu nu times G lower mu nu is given by the identity matrix, or the Kronecker delta symbol. Indeed, this is the equation which defines the inverse G mu nu. And this guy here is a 0, 2 tensor. This guy here is a 1, 1 tensor. And this guy here is a 2, 0 tensor. Likewise, the left inverse of a matrix is the same as the right index of the matrix. So when you contract either the first or the second indices, you get the Kronecker delta symbol. I will now introduce one final bit of notation before ending, which is the following. So what I will do is I will use G mu nu and G upper mu nu to raise and lower indices. So, for example, if I have a vector v mu, then I could contract it with one index of the metric to get a one form v nu. Likewise, if I have a one form omega mu, I could contract one of its indices with the inverse metric to get a vector that I would call omega nu. So in your classes on multivariable calculus, for example, and in your previous physics classes, you have not been careful to distinguish between upper and lower indices. Why did it not matter that you weren't careful to distinguish between upper and lower indices? It didn't matter because you had a flat matrix, which was the identity matrix, which meant that you could raise and lower indices using this rule at no cost. You're just multiplying things by the identity matrix. When we consider Minkowski space, where the metric has a minus sign, or when we consider curved space, where the metric is no longer flat, then it's important to be careful with this rule about how we raise and lower indices. So I'll stop here unless there are any questions. All right, see you on Monday.